As a general rule, if I have two surfaces and intersect them, much of the time I'm going to get a curve. Now, that's not always the case. I could, for example, have a plane and a sphere. These don't intersect at all. If the sphere is sitting exactly on top of the plane, they would intersect at a single point. But if I intersect this plane with this sphere, now you have to pretend that you just have to pretend, okay? I would be getting essentially a circle, okay? And very often that's going to be the case. That's a very common way for curves to arise as the intersection of two surfaces. We took huge advantage of that fact when we were graphing our quadric surfaces, because we said, okay, we've got this quadric surface, we've got this equation in 3 variables, it's going to be some sort of a surface. What does it look like? We intersected that with planes. We strategically chose planes parallel to the coordinate planes through the center, and we looked at the curves that we got. For a quadric surface, those were conic sections. Okay. So what I want to do here is I want to see if given two surfaces, we can come up with a way of parametrizing the curve of intersection. So I'm saying we're going to have this paraboloid, z equals x squared plus y squared, and this plane, x plus y equals 1. Now I've told you it's a plane, so it's in 3 space. It's not the line in the xy plane, it's the extrusion of that line, which would be a plane in 3 space. Okay, so when I have two surfaces, I basically have 2 equations in my 3 variables, x, y, and z. This one just doesn't happen to have any z's in the formula. 2 equations, 3 unknowns. So I have 1 more unknown than I have equations. That helps to explain why we're going to get a one-dimensional object. I don't have enough information with just 2 equations and 3 unknowns to get things down to a single point in most cases. But I can generally get things down to a single variable. I can reduce the number of variables necessary to describe the intersection of these things. So the goal is to describe the points x, y, z that are on both surfaces in terms of a single variable, which we'll ultimately call our parameter t. Okay. Often, the simplest way to do that is to choose one of your variables, x, y, or z, and try to describe the other 2 in terms of that. Now, in this case, I'm going to start with this equation, because x and y show up in both of them. I could easily solve for y, and I could say y is just 1 minus x. So I've described y in terms of x. Now, since I've described z here in terms of x and y, but I can describe y in terms of x, I could then say z is x squared plus 1 minus x squared. And obviously, I can describe x in terms of x because it's just x. So I've described all 3 variables in terms of 1 variable. Here I'm calling it x. What I'm going to do is I'm going to simply let x equal t. I'm going to let that be my parameter, and then I could say r of t would be t, 1 minus t, t squared plus the quantity 1 minus t squared. That way I have described as a vector function the curve of intersection of these 2 surfaces. Okay. I can see, by the way, from this equation that the entire curve lies on this plane, because that's the x value and that's the y value. And if I add them together, t plus 1 minus t, yep, that does give me 1. I can see that this does lie on the paraboloid, because this is my z value, and notice it is my x value squared plus my y value squared. So I can see a connection between the equations. Now, in this case, I used a trick which is often the simplest way to go, to simply let one of my 3 variables, x, y, or z, be the parameter. It's not necessarily always going to be possible to do that. Let's just say I wanted to look at the curve of intersection of the unit sphere and the plane y equals 1/2. Now I can actually visualize that very easily, because I know if I intersect a sphere with any plane, I'm just going to be getting a circle. Okay, so this is just a circle in the plane y equals 1/2. But if I go to parameterize it, the equation of the unit sphere would be x squared plus y squared plus z squared is equal to 1. Now obviously my y is pretty easy because that's just going to be constant at 1/2. But if I were to try to let x be t and solve for z in terms of that, let's just try solving for z in terms of x. So I've got x squared plus 1/2 squared plus z squared equals 1. Okay. Now that's going to be just 1/4. So I could solve for z squared. Z squared would be 3/4, just subtracting that over, and then I'll subtract over the x squared. Okay. Now I'm not going to be able to solve for z in terms of x, because z can be either positive or negative, so I would get two different options. And if I tried to instead solve for x in terms of z, I'd run into the same problem. So if I have too many variables squared, I may not be able to simply choose one of my variables to be the parameter to describe this parametric curve. However, that's not to say that I couldn't parameterize this, because I know that if I do plug in this 1/2 for y, I can keep this as x squared plus z squared is equal to 3/4, keeping the x and z on this side, replacing y with 1/2 and just moving that over. Well, I know what that is. That's just a circle of radius √3/2. Remember, this would be the radius squared. So I know how to parameterize a circle. What I'm going to do is say y is constant at 1/2. In the xz plane, I need to be parameterizing a circle of radius √3/2. So I'm just going to take my unit circle and scale by √3/2. So let's try √3/2 cosine t, √3/2 sine t. That would do it. Now, with both of these examples, in coming up with the parameterization, I've introduced an orientation to the curve. The orientation wasn't an inherent part of the curve of intersection. So my answers here are not unique. I could certainly have put the sines here and the cosines here. There are probably lots of other ways to parameterize these things. So parameterizations of curves are not necessarily unique, and sometimes the orientation is really important for a problem. Sometimes it's just sort of incidental. Oops, couldn't help but introduce one when I parameterized this curve, but I was really just concerned with getting the points that were on the circle in that particular case.